lesson on superposition of waves, and when I mean superposition, what I'm talking about is how waves add together in different phases. So we could either look at waves that add together in phase at the same time, in which that produces a very large resultant wave, or we could look at how waves add together out of phase, in which case they diminish and you get no wave as a result. Okay, so we're looking at this special case which is called Young's double slit experiment. Young's double slit experiment. And it's usually conducted with light, but this effect also happens with sound. So any wave will undergo will experience this type of phenomenon. Okay then, so it's double slit, so that implies that there are two gaps which waves are able to propagate through. So here are the two gaps. And each of these gaps produces a wave. A nice continuous wave of equal wavelength. So each of these have the same wavelength and therefore the same frequency. But through both holes we're getting the same wave. And you know that through an aperture waves will start to diffract out. And if this continues all the way to a screen at the far end, then what you start to see from the center point, all of the waves, if I've drawn it really well, all of these waves along the middle will constructively interfere, just like this instance at the top, and so therefore, if this is with light, we have a bright patch. If it's with sound, we have a loud patch, etc., etc. There will be a patch along here where the peaks join with the troughs as we get there, and that will be a dark patch, or if it was sound, a quiet patch. And this happens from the center out in successive bright, dark, bright, dark, bright, dark, and bright again. And what we need to ask ourselves is why? How do we change from this setup here to this setup here when we're using the same sources? They're the identical wavelengths. Where does this phase change come about from? Well, let's make that diagram a little bit simpler, and rather than drawing in every wave, let's just draw in the ray which is coming out. Okay, so the same setup again. Let me just draw this nice dotted line as a center point. And let's ask, first of all, why do we get this bright patch just here? Let's draw in the ray of light coming from both sides. And let's ask ourselves why there's a bright patch there. Well, this ray of light is traveling along like that, and it reaches this point in phase with the ray of light coming from this side. So what we can see is that from this point here, these rays must be in phase with each other, and they continue to go into phase until they get to the screen, and therefore it's a bright patch. So what's going on in this part here? You see, the same part of the same light doesn't actually have to strike at the same point, but the same phase has to strike at the same point. Okay, so we've got this extra little bit of distance travelled by one of the waves as opposed to the other, and this we call the path difference. Or, if you like, the PD, not to be confused with potential difference. Now, if that is a whole number of wavelengths, n being a whole number, obviously lambda is the wavelength, then that would suggest that the wave will be in phase at this point with the other one and therefore become a bright patch in constructive interference. So PD is a whole number of wavelengths, and that is the crucial understanding of how we get the bright patch there. Okay, let's work out exactly what's going on here. by zooming it up and taking a look at the geometry of what's going on inside that dotted box. Okay, we have one ray of light shining off in that direction and the other ray of light shining off in that direction to meet later on as they hit the screen. Okay, let's just take a look at that. So this is a right angle, so making that a right angle triangle inside, this being angle theta. We give the separation of the two slits the symbol d, and so therefore our path difference along this side is merely a simple trigonometric ratio. We can say to ourselves that the opposite angle and the hypotenuse is known the opposite we want to work out. So therefore, if we write down our sine identity, opposite is the path difference, the hypotenuse is d, giving us d sine theta is the path difference, which has to be a whole number of wavelengths, or indeed d sine theta is n lambda. Now that is the condition for Young's double slit experiment. However, there's one problem here, is that that's not very easy to measure, sine of theta. How on earth do you measure this angle in here, which, and I'll just show you now, is the same as this angle here? How do you measure that angle which is projected towards a screen in distance? It's not very easy at all. So what we need to do is we need to work this angle out in terms of measurable laboratory conditions. So what we do is we say, well, actually the distance between the screen and the slits is very easy to measure, length L, and also the bright patch from the central maximum, or the centre of the entire experiment, x, is very easy to measure. We need to understand a nice little trick, that being that sine of theta is approximately tan of theta when theta is small. You can prove this to yourself if you like, because you can type it into a calculator, sine of 1 degree, tan of 1 degree, and see how large you get before this becomes untenable. But the trick, and the reason why it's really useful, is because tan of theta is the opposite over the adjacent, the length, or x over L. So therefore, how about let's rewrite our identity. So let me rewrite the identity here in its most fundamental form, or let me rewrite the identity as x over L, whereby I've replaced sine theta x over L. It's a whole number of wavelengths. There we go. So this is the equation you need to become comfortable with and understanding how it comes about. Okay, I suppose one last thing I ought to mention is this n, the whole number of wavelengths, which we talked about here. If it's one wavelength, we hit our first bright patch. If n is 2 wavelengths out, then we reach our second bright patch. N is 3, 4, 5, 6, and so on and so forth. Okay, with that in mind, we are going to try a simple question, and let's see how we can put this equation to practice. Okay, I'm going to simplify these pictures a lot more, because we're going to have to draw over them quite a lot. Example number 1. Okay, we have a slit separation of 0.4 millimeters. So this is very small, so now we're dealing with light here. We have a screen which is at 600 millimeters separation from the slits. None of this is drawn to scale, by the way. And the 10th bright patch, so this is where n equals 10, is at a separation of 7.5 millimeters. Good, now the question is here, what type of wavelength of radiation is being used in this situation? So let's just go straight back to the equation that we had before. We said dx over L is m lambda, and we're looking for lambda, which is dx over ml. This should be quite straightforward. All we're going to do is substitute in the values. D is 0.4. And be careful here, because they're all in millimeters, does not mean that we can just leave them in millimeters, because you'll see why. We actually have two lots of millimeters at the top and one below. So, all intents and purposes, keep it in standard, in SI units. So we have 0.4 millimeters. Multiply that by 7.5 millimeters. Divide it by, well, we're on our 10th position, our 10th bright patch, and 600 millimeters. And when we tap that into the calculator, I very much hope we come up with 5 times 10 to the minus 7 meters. Good, okay then, right, now let's try tweaking a few things with that experiment to see what might happen to the fringe separation. Okay, so the first tweak, let's reduce the fringe separation to being 0.2 of a millimeter. So we're changing D. If this is being squeezed, then what's going to happen to the fringe separation on the screen? You might have your own suspicions. Let's get the maths working and seeing what happens as a result. So let's start with our original equation. We're now looking for the separation. Plug in all other values, like we did before. So we have our 10th maxima. Our wavelength of light is now known. And our separation from the screen is 600 millimeters. Divide that all by our distance, which is now 0.2 millimeters. And that gives us a value of yes, because we're looking for the 10th separation, 15 millimeters. So what does that mean? Well, that means that if you halve the distance here, you've doubled the separation from the central maxima, which you can pretty much see in this equation anyway. Because it's proportional to 1 over d, if you halve 1 over d, you're going to double what you've got before. Okay, let's do one that's not so obvious. Let's the second part. What happens if we move the screen away? So we're now at 800 millimeters, keeping all the other examples the same from the first, so 0.4 separation, etc., etc. So therefore, let's trust the maths of the equation. Start with our original equation. We are now looking for the separation again of the 10th maximum, just like before, given a few changes, but the same wavelength as before. So our 10th maxima, our wavelength at 5 times 10 to the minus 7 meters. The length now has changed to 800 millimeters, but we're still using 0.4 millimeters as our separation. And that gives us, if I'm not mistaken, 0.01 of a meter, which is approximately, well, it is 10 millimeters. So what's happened is, as we've increased this distance, so the separation has increased. And that would suggest, right, because in actual fact what's going on here is, this is the angle theta. We're keeping theta the same, and if you stretch that adjacent length, so the opposite length must change as well. So intuitively you've got a suspicion that that's what would have happened. Right, okay, C. What happens now if we use red light? And red light has a wavelength of, and interestingly they will give you wavelengths in terms of nanometers. And what you should realise is that is 7 times 700 times 10 to the minus 9, which is the same as 7 times 10 to the minus 7 meters. Okay then, red light, everything else remaining the same. Let's plug in, let's start with our original equation. You are looking for the separation again. The 10th maximum, our wavelength of light has changed. We are using the original length in the original setup at 600 millimeters, and our separation in the original setup is 0.4 millimeters, and that gives us an answer of 0.0105, 10.5 millimeters. So what's happened is we have, by using a lower wavelength of light, we have now increased gap size. Good, so hopefully you followed that maths through. Let's have one more go at one more question, but this time I'm going to let you have a go at it. I'll set it up and then you can see whether you can solve it. So example 2. Okay, I'm going to use the same setup as before. 2 slits, a screen not drawn to scale. We've got 0.3 of a millimeter separation between the slits, 1.2 meter between the screen, and 2.4 millimeters for the first maxima. And the question is, what is the wavelength of this light used? By the way, this is a sodium light, and sodium light is that which is used in the light bulbs, the street lights. Okay, so what's the wavelength? So if you think you know, hit pause, give it a go. If not, I'm going to launch straight into the answer. Okay, let's start off with the equation that we started with in the first instance. So let's say x over L is n lambda over d. I believe that's right. Yes, and then we are looking for lambda, which is x d over n L. X is our separation at the screen, 2.4 millimeters. D is our separation of the slits, 0.3 times 10 to the minus 3. Obviously we're using the first maxima, and our length is 1.2 meters. This gives us 6 times 10 to the minus 7 meters, or 600 nanometers. Excellent. Okay then, now let's second part to this question. Let's say that on the screen, for all else being equal, 1.2 meters, we're using the sodium light, but now we get a separation of 7.2 millimeters for n equals 2. What is the separation of the slits? So D equals what? If you think you know, press pause and give it a go, otherwise I'll run through the solution right now. Okay, let's start from where we were before. Let's rearrange it to get our separation D. All other things are being the same, but this time there's a few complications. We've got second maximum. We are using the same light as before. the lengths remain the same, but this time we have 7.2 millimeters. And so therefore, I believe the separation is going to be 2 times 10 to the minus 4 millimeters, or 0.2 millimeters. Sorry, that's 2 times 10 to the minus 4 meters, or 0.2 millimeters. Right.